By the year 2030, advanced fighters with fifth-generation characteristics, such as greatly reduced radar cross-section, supersonic cruise speed, advanced radar and IR sensors, long-range air-to-air weapons, extreme agility, and robust network connectivity will be in service in many countries. Here we envision a notional group of 8 such enemy aircraft. If U.S. aircraft are equipped with IR sensors capable of detecting enemy fighter aircraft traveling at Mach 1.8 at ranges of 150 nautical miles or more, then we can see the region in which they are detectable illustrated here. In contrast, to minimize the effective range of enemy sensors while maximizing their own, it might be advantageous to design future long-range U.S. aircraft to fly at subsonic speeds and have improved stealth characteristics as well as greater payload capacity, power, and cooling capacity. It may also be possible to utilize these future platforms as airborne command centers for a distributed complex of U.S. sensors and shooters. Robust line-of-sight network links between large manned U.S. long-range aircraft and smaller, highly capable unmanned aircraft would allow them to function as a distributed weapons system by sharing data and coordinating their operations. As you can see, the subsonic unmanned aircraft have greater range and payload capacities than the opposing manned fighters due to their subsonic speeds and less stressing maneuverability requirements. Like in the previous illustration of the detectable area of the enemy fighters, the area where U.S. aircraft could be detected by opposing aircraft infrared sensors is illustrated here. Note that while the detection range is different for the large and small aircraft due to their size, both have ranges that are much shorter than supercruising enemy fighters. For simplicity's sake, we will combine these ranges into a single vulnerable area. Putting both groups of aircraft together, we might find a situation that looks something like this. The supercruising enemy fighter group and long-range U.S. aircraft are approaching each other at a combined speed of about Mach 2.6. Things happen quickly at this speed, and even though the aircraft began over 350 nautical miles apart, they're on the verge of an encounter within minutes. At this point, the U.S. aircraft are able to detect and begin tracking the opposing fighters, but can't in turn be detected. This bestows a commanding advantage in situational awareness. Within a few seconds, the data they collect is fused and distributed across the entire network of U.S. aircraft. The human crew on board the larger aircraft are able to assess the situation and direct the unmanned aircraft via simple point-and-click commands. The human crew assigns targets. The unmanned aircraft are directed to turn 90 degrees right to delay detection by the opposing fighters. In this case, the human crew elected to engage each opposing fighter with 2 very long-range missiles. The large aircraft fires a total of 16 missiles at the opposing formation. Assuming a single-shot probability of kill, or PK, of 0.5 for each of these missiles, we can expect 6 of the 8 opposing fighters will be destroyed before they are able to detect any U.S. aircraft. If the surviving enemy aircraft elect to continue their search for U.S. aircraft, the human crew has ample time to reassess the situation. And in this case, retarget and direct 2 of the unmanned aircraft to fire 2 AMRAAM-class missiles at each remaining enemy fighter. Again, assuming a 0.5 single-shot PK for these missiles, we can assume that both of the remaining aircraft are destroyed. In this example, 5 U.S. aircraft have destroyed 8 advanced enemy fighters without a single U.S. aircraft being detected. This satisfies the first look, first shot, first kill criteria. This is accomplished by exploiting large aperture sensors for superior information acquisition and longer-range weapons to achieve superior situational awareness and leveraging minimal radar and IR signatures for better information denial. The advent of airborne directed energy weapons would only increase the advantages of larger and/or subsonic aircraft. For more information about this concept and the research used to develop it, see the 2015 CSBA report, Trends in Air-to-Air Combat, Implications for Future Air Superiority, and please visit us at csbaonline.org.